Okay, so let's talk about the new material. So today we will talk about logistic regression, which is one of the very important material in practical machine learning. So this is the notebook. I think I already uploaded to the surprise space. So let me connect that. Run one time. So I'm going to load all these require the library. So particularly, so for the logistic regression, it's in the linear model. It's a logistic regression and the logistic and the logistic regression DV. So these are all very important. So this is data that we're going to use. Okay, so first thing, let's read this data. So you can see this is actually the data. It has so the data has 118 chips. These are the results of 2 tests of quality control and information whether this micro chip will went into production or not. This variable already centered, so you don't need to and recenter that. And the column value and its own mean value are subtracted. So that means I already normalize that. So the average like microchip and corresponding to the 0 values of the test and the results. So you can see everything is just pre-processed very well. You don't need to worry about that. So there are a couple of things. So we are going to try different regularizations in the logistic regressions. And also we will try, the logistic regressions with various and regularization parameters. Okay, so so we were using this like logistic regressions and we were using this regularization to test and various regularization parameters to test the separation border, and you can have some senses of underfitting and overfitting. Then we will using the cross validation and the grid search to find out the optimal value of the and regularization parameters. Okay, so let's have a look of this data. So we have X data, we have a Y data. So X has 2 dimensions. So that we can actually plot that in the 2D plane, which is test 1 and test 2. And so for the release, it has like 2 different labels. One is release, one is faulty. So basically, there is a separation like curve, and there's a curve that separates these 2. So basically, if we do that, you can see this looks like this. So and obviously, from this 2D plane, you can see this separation curve looks like a circle. So this is not and not linearly separable. Okay. So this is some help functions to actually help us to plot this boundaries and separation boundaries. You don't need to worry about that. Okay, so this is very important, and obviously in the most of cases you don't know and what kind of and what is the best curve to separate these 2 and to separate these 2 points. And what we can do is we can using this polynomial features of degree D. So that means I'm going to lift this variable from low dimension into high dimensions. So this is basically, and you can see these are all and all possible polynomial features with the polynomial of degree of d, so x1 power d, x1 power of d minus 1 times x2, and so on. So this is all the polynomial features. And these features, and particularly I plus j equal to d. So that means this has exactly the degree d of polynomial features. As a remark, so if d equal to 3, so these are all the features that is less equal than d. Right, so we have 0th order, we have a first order, we have and a second order, and we have a third order, right? So this is and this is what we are getting here. Okay. So so we can keep going. We can keep getting the d equal to 4, d equal to 5 until to d equal to 10. But this number of features will be exponentially large. So sometimes you probably don't need it. It's like too big sometimes. So and for this cases, let's try something that is, say, polynomial features up to the degree of 7. Right. So and degree 0 to degree of 7. So this is that many of features that we're trying to actually to get. So if you look this polynomial here, you can see this is just a polynomial feature. So we can, using this poly fit transform of my data, and data is x1 and x2. If you do that, you will find out my periods only have two features. Now it becomes 36 features, right? So that's a cool, and that is quite a lot. Okay, so let's train our and the logistic regressions with first is a regularization is 10 is and 0.01. So this is one of the things that we are getting. You see, we are actually getting a curve. But the accuracy of training is not very good. You can see this, and this and the separation curve actually is shifted. It's shifted to the left. So that's not really ideal. So it doesn't give you a very good an accuracy in training. So that means my C is probably too small. Okay, let's try a larger one. So then I'm going to try C equal to 1. Okay, so so this is something that is and it's slightly different because I think in search the logistic regression, scikit-learn, and tell all these help menu right here. So this C is penalty. It's the inverse of regularization and the strength. So that means the larger of this value, the smaller of the regularizations. So the smaller of the C and the larger of the regularizations. So this is kind of the opposite of what we think about the regularization. C is actually the inverse of the regularizations. Okay. So, and we can try to increase C into 1, which is the default value in the logistic regression. So this is, in fact, we weaken the regularization. Now this time you can see our accuracy is actually better. So you can see this has a better separations now. Okay, the accuracy is 83.1%, which is really good. Okay, so let's see, can we increase the C a little bit more? So if we keep increasing the C, that just indicate we are going to make the regularization smaller and smaller. Okay, so okay, just a second. Okay, sorry about that. So if we increase the C even more, that means we don't have very strong regularization. So if we choose C equal to 10,000, you can see this actually give you a very much open-ended curve to separate these things. But of course, in these cases, we know the training set accuracy is getting even larger just because it's trying to fit, trying to separate everything as possible. But you can see this doesn't work very well because there are a lot of unnecessary zigzags here. This to indicate it might have overfittings. And although my accuracy of training set is increases, but that doesn't mean anything because if we have a testing data set, this accuracy will drop just because of overfitting issues that we are having. All right. So so this just give you some idea what is the effect of the C, which is the inverse of the regularization, and it look like. So what is that? I mean, to be more precise, is you can think about this circular is trying to do the following an optimization that we have 1 over C as being the strength of the regularizations. So here we are using L2 and regularization, which is the which is the norm of the parameter here. Okay. All right. C is basically the inverse of regularization, as I mentioned. All right. So if you have larger in terms of parameter, then the more complex of the relations that you can recover. So you can think about C as being like complexity of the model. If the larger of C, then the model will be more complex as model and it has larger like model complexity and the model and capacity. But if your regularization is too strong, that means your C is really small. Then you are trying to and the solution just being and make the weight and to be very small. So that will not sufficiently penalize all the errors because you're just trying to shrink as much weight as possible. So this is like something that you will have like underfit, and you are getting a circle. That's right, but the issue is this circle is not centered in the right places. Okay, being shifted in the wrong domains. So this is clearly the situation of underfitting. This has been the situation of overfitting. Okay. So this is basically the balance between the C's, and you cannot choose your C very large. You cannot choose C to be fit and small. Each time you have to find out the optimal C based on your problems. So that means you cannot like predetermine such kind of C. That means this is a model hyperparameter that has been tuned through the cross validations, like what we did for the maximum depth in the anti-decision tree problems. Okay, so and we can do the following. So we can do this cross validations. So basically, so we can do the grid search of this 500 C values in the log scale. So I mean, this is basically and 10 to the minus 2 to 10 to the 3. So and 0.01 to 1,000. Okay. in log scale. So these are the parameters that you're going to search, and which is C values. And you're going to put in this CS, this CV here. You're going to plug in this and a stratified K-fold. This is already being outputted from here, SKF. So you pre-created those K-fold cross validations, and you plug in this CV equal to SKF, CS equal to this C values. Then this is basically the logistic regressions, CV and cross validations. And the logistic searcher. So this is basically you predefine your and cross validations and the searcher. Then you fit in this polynomial features and the Y features. Right, so this is basically, and you have data and you have fit. So basically they will do the 5-fold cross validations for all these like 500 and for all these 500 C's. And I choose n job equal to -1. That means I'm trying to parallel as much as possible. So here we have 2 workers. That means 2 CPUs. It will do these things for you automatically. Okay. So the optimal C is given here. So from this 5-fold cross validations, this optimal C gives 150. Okay? The one of the very important things. Okay, so I mean, and you want to see all the accuracies in terms of the cross validation C's value, you can just plot it out as the following. I mean, everything just, stored in the score and underline 1. So this is already give you and all these values here, but it's given as 5 by 1 500 and scores because we are doing 5-fold cross validations. So that means I have 5 scores. Right? So that means for 5 scores, I'm taking the average of these 5 scores. So it actually gives me the mean value of this 5-fold. So you can see this actually give you these kind of values. So it starts to shoot up, then zigzag, and stop right here. I think the best region is somewhere here, right? And give you like the C is about 150s. And gradually it start to decrease. Okay. So the reason that it actually decreases is because of the overfittings. So this is actually very interesting because so you can see this very simple example on the logistic regression with the polynomial features. You can see some like overfittings and underfitting issues. So these type of like overfitting and underfittings shows up all the time. And the reason that this is so important is because for the K-fold cross validations, if you're just using the way that I'm doing here, you just take all the data, you just get in the training accuracies. So you'll find out, okay, I should and keep increasing like the C, and the training and accuracy start to increase all the time. But the K-fold says I'm going to using the part of data to train and the rest to test, and then can mimic the idea of the generalization error. So that's why and we are always trying to predict and mimic the idea of the generalization error. So you can see the effect of the overfittings. And otherwise, you are just using the training data set. Training data set, basically tells you nothing. Okay. Okay, so that's good. And also, you can also and then select the yes, and we already and get this values here. So it's quite good already. And you can also limit into like in 0 to 10 to see those values in the before, because we are taking the log scales, right? So that means we have a more point beforehand than later. So if you limit your x limit from 0 to 10, you're getting the value like this. So this is the cross-validation curve. So this is something like you have your parameter and you have your mean of your cross-validation accuracies. And you can build it manually, and scikit-learn has this special method to construct that. And then we can use that going forward, right? So, and also when the logistic regression is good, when will be not. Okay, so, and let's try different data set, and then we will see some effect when this will be good, when this will be bad. So this is something called sentimental analysis, which is very important in machine learning. So this actually data of the binary classification of IMDb movie reviews. We have a training set, it's marked as reviews, which has 12,500 reviews. Marked is good, and there's another 12,500 marked is bad. It's not, I mean, it doesn't seem very easy to start with because they are all word, right? So here is what we have talked about, how to transform the text into simple vectors. But it's by using something called bag of words. So basically, just a quick review of what I'm talking about. This is, for example, if you are talking about this is how you get ends. So, and what you do is you tokenize, it becomes this is how you get ends. Then you build a vocabulary over all the documents from A to Z. So this is the whole your dictionary. Then encode this sentences with this kind of sparse matrix encoding. Then everything for the ends becomes 1, and the corresponding gets becomes 1, u becomes more, and so on. So this becomes a very sparse and a vector, and you have all the word of all these like and movie reviews, and you are going to encode them into those sparse vectors. Okay, so here is what I'm doing. So I'm going to download this data. So so you don't need to know how this actually is doing. This is a very, very much a very like well studied so data set given from Stanford. So we are just downloading the data and loading the data. Slow. Okay, good. So let's print out the training data. The first things we will have like 12,500 training data and 12 and so basically the so training and testing, they are all like and 250,000, and you have and 50% being positive and 50% being negative, right? So these are a few examples. So for example, words cannot describe how bad this movie is. I cannot explain it by writing only. You have to see it for yourself to get a grip how horrible a movie really can be. Not that I recommend you to do that. There's so many glitches and so on. You can see this is obviously a very negative reviews. So that's why the y train of that value is just 0. 0 means it's negative. Okay. So you can do for the second one is everyone plays their part pretty well in this little nice movie and so on. So you can write here and you can read this. This is pretty much a very positive movie. So you can see this review is very positive. It's very good. It's very good. Okay, so you can see from Y train, so it's actually 1. So that means it tells you this is a very positive reviews. Okay, so how can we do and back of words? So you can do count vectorize, right? So you can do counter vectorize. So we have feature extraction, the text of counter vectorize. And so, this CV, it's not cross validation anymore. It just has the same name for the counter vectorize. Then you fit the text train, so the training data. So if you fit the train, you find out I have almost like 75,000 and the vocabularies. Okay, so that is quite a lot. If we actually look those words, and what you can do is you can like read those words, like get the features out for the first and for the first 50s and something in the middle. So you can see they are listed alphabetic orders. Okay, so and also we don't actually care about and a lot of grammars. For example, pinks maybe should be the same thing. Pineapples should be the same thing. All these stemming and the stemmingization and the lamalization, I don't care. Just this is the simplest model that I work with. Okay, so of course you can load more complicated and the natural language processing packages that can process these things automatically for you. Okay, so I want to remind you this is fit. Then you do the transform on the text train. Okay, so you transform this data becomes and encode these sentences into sparse vectors. Okay. So if this is your sentence, this and the movie is terrible, but it has a good effect. You can see this actually give you a 1 by 75,000 sparse vectors. It is stored. It's actually stored in the element in CSR format, compressed sparse row format. So this is some format that being used a lot. And in fact, in homework, you are going to use that. So you can count how many non-zeros you have. And you see, I will have 10 non-zero values. So these are corresponding and indices in these vectors are non-zeros. So because the best way to store a sparse vector, sparse matrix, is I don't keep track of all these zero, because maybe 99.9% of part of matrix is actually zero. Only 0.1% is non-zero. So so I only keep those 10 stored and indices that give you non-zeros just once. Okay. Okay, so you got some value like this. All right. So then you can and apply the same operation on the testing. So here I want to emphasize you never actually want to fit the testing data set. You can only using what you've learned in this count values to transform this test. Sometimes you might have some word in the tested data set is out scope of the training data set. So we have like more vocabularies than the training data set. That's totally possible. If those words shows up, what you can do is you can just automatically transform into something called unknown, right? So some word that shows up in the testing data set, but it's not showing up in training data set. That means I don't have any information about this word, so I'm going to and just assign this into unknowns. So here is what I'm going to do. So this is pre-processing, and we know it's very important to pre-process the data. And, so the next step is we have this training and the training. So X train and Y train. So and what you do is you just train your logistic regressions. Okay. So these are basic tells you and what kind of software you want to use. Here you are just automatically trying to parallel that. So let's and see the so we can try and test the training and the testing. So the training error will be 98%. Here, if you want to do some testing, you can just automatically say, and that like, and the logit dot score and input the training and the testing and data, it will automatically process and to do like predictions for the models and compare with the ground truth. And of course, you can also do like and the legit and predict of an X test. Then get your Y predict, and then you're using score to compare the testing data set and versus predict. That's the same thing. It's just like scikit-learn give you multiple ways to do. I mean, so exactly the same kind of stuff. So this give you and a little bit like short-handed version of everything. So this is 86% for testing data set. And you can see the testing data set is not super good. And I want to remind you here, if you don't specify any of the C, this is automatically to true C equal to 1. So I didn't do any cross validations for the C's. So basically, this is the so the C is equal to 1. Okay, so this is some like function that to plot. So we can see those features and to see like and to plot these features and which features has like larger weight and the less and which feature has a lower weight. So these are the top, I believe, the top 25 positive and like top 12 and the least 25. So this is the least and the like the most negative one, and this is the most positive one, and the weight corresponding to those words. And for example, this is rare, funniest, and refreshing and wonderfully. So these are all and assigned to have very high and a positive value. So that means if this like review has all these words, that means it's very likely this will be a very positive reviews. On the other hand, if you see these kind of words here, the waste, disappointed, poorly, lacks mass, it's very likely this movie review will be very negative, to be 0. Okay. So here is And you can make the whole thing, to pipeline. And I already mentioned about the pipeline. So that means you don't need to go through these things. And again, if your data is being changed, right? So this is very important. The point of the pipeline is once you set up the pipeline, so you can push your data in, and you can change your data, and you can keep the same pipeline, and you can get, this result and quickly. So, in my pipeline, there are only two things. One is we do this count vectorize, which is we turn into text into vectors by using and bags of words. The second thing is we just apply the logistic regressions of this data set. All right. So here is what we can do, and we can do this testing to see how fast of this running for this data set, which is quite data and quite big. So you can see right here. So we basically got the, same result for the testing data set. And you can see this runs very fast. Colab, it would take about 16 seconds, which is pretty impressive compared I'm actually have to process such a large data set. Okay, so, and again, we didn't do any cross-validation to find out the best C. In fact, we need to do it, right? So this is obviously a very important component. So here is the way and to do it, and this is, and basically, first thing that you need to set up is your parameter. So your parameter here is I'm going to plug in this and a logistic regression. So basically, I'm going to do the cross validations for this pipeline, but this pipeline has two components. The first component is count vectorize. We didn't do any cross validation for that part. We only need to do cross validation for this logistic regressions. And in terms of logistic regression, the parameter that we actually needed to tune is the C, right? So that's why you have a double dash and double underline to indicate I'm going to hyperparameter tuning of C for the logistic regressions, okay? Then you have this, and you have to set a domain, which is a log space. Usually what we do is, we always choose everything in terms of log space of from 10 to the minus 5 to 10 to 0, which is 1. And due to the constraint that we have, we only do it for the 6 values. Here, what we do is we choose the cross validation as a 3, and the 3-fold, and to do discrete search. So why we choose this way? So and we choose 3-fold, and we only choose 6 different values of C's, because we know with that would take about 18 different rounds, right? Because 3 times 6, that's 18 different rounds. But we know for each round, that would take about 16 seconds. 16 seconds times 18. That's a quite a bit time of waiting. So that's why you actually have to go through these things to see how much and how long does it take to run one time. Then you can, based on this, how long does it take on running one time, then you can just to see how and how long does it take to actually run this cross validations, and how much longer that you can afford, right? So if you choose this, it's not 6 rather than 60. If you choose not 3 but 5, then probably you have to wait for hours. that you don't know why. Right? So that's why this block of 35 is very important to give you some idea how long does it take for a single run. Then later on, then you have to run this like 18 times or 100 times, that you can wisely to allocate how many folds that you needed and how many C's that you want to search, right? So this is a balanced way, because you have limited budget. You cannot use your problems and use like all your time and all your energy to solve that problem. You have to use your resources wisely. And you can see here take about 2 minutes. So the best parameter that we got is 0.1. Since we only do a search from 10 to the minus 5, 10 to the minus 4, 10 to the minus 3, 10 to the minus 2, 10 to the minus 1, 10 to the 0. Okay, so the score that we got is 86, which is better than 86, which is a 2% better than that. Okay, let's see. Okay, so this gives you some idea. You can see with the different CSC, when it start to increase, that means my regularization is start to weaker and weaker. And my training accuracy is that always increases and without any doubt, but my testing start to show some and it declines, right? So it start to increase, then declines. So this is very and reasonable and very normal in these cases. Just a second. For the testing data set, and we can see this is all these results that you got. Okay. So this grid search tells you this. So like grid and the legit, we're always using the best and the best C. And since you already find out the best C, they're only using the best C to do any kind of prediction for this testing data set. All right. So this gives me like 88%, and very similar in the result. And you can do the same thing for the random forest. But random forest will take much longer time to do so. But I don't want to spend too much time on this. And you can run it at home. So another commonly asked question is, and what kind of data set actually this kind of linear models or logistic regression will fail, right? Getting really worse, right? And how can we handle that? So one of the example is, a famous example is called XOR problem. That means the data set has two classes. One class is like this, and another class is like this. Obviously, there's no way I can separate that with a straight line, and you actually have to using curve to separate these two in a set. So that means this is a very simple binary classifications, but you actually have to using and highly nonlinear ways to separate these two data sets. Okay, so if we just using create a data like that, if we just trying to do the logistic regression on this data set. Okay, so this is a commonly used data set. So here is what I'm going to do. I'm going to apply this and the logistic regression by default, all the values by default. This X is the X that we are getting. The Y is the Y. This is 0. This is 1. This XOR problem. So, and here's what I'm gonna get. You're gonna get everything beyond here is being colored as red. Everything below that will be colored as blue. And obviously that's really bad, because as you can see, the error that you got is almost like 50% of error. right? So this is not good and really bad. But we can simply trying to incorporate and lift the feature into high dimensions, and say we lift the feature into polynomial features up to degree of 2. Then this problem will be solved. So here is what I'm going to do. I'm going to create the polynomial features with degree up to 2. Then you apply this logistic regressions. You can see this actually separate this data very well. So everything in this region will be red. Everything, this region will be blue. Okay, so very, very efficient. So that means a lot of time. So this is also common. As I said, this is commonly asked questions in the interviews to construct a data that a linear and a logistic regression just fails miserably. So one of the example is XOR. And the next follow-up question is, can you construct a method to modify, logistic regressions to make it work? So the way to do it is, all you need to do is to take this polynomial features of the data, then you just take the polynomial features up to the degree of 2, and then you put in a pipeline as pre-processing or feature engineering of your features. Then you apply this logistic regressions. Then you can perfectly separate this XOR problems. So these kind of the power is, you can think about and lift our and original features in lower dimension into higher dimensions. Maybe higher dimensions they will be linearly separable, but in the lower dimensions they are only non-linearly separable. So in fact, this with a degree up to 2, this is only like 6-dimension feature spaces. You can see 1, x1, x2. So these are the original features. These are the 3 additional features that we create: x1 square, x2 square, x1, x2. But of course, if we want to project it into original feature spaces, then the boundary will be and obviously nonlinear, because we have terms of x1 square, x2 square, and x1 times x2. So this is also the point of and a starting point of why we need these kind of and polynomial features. And but in practice, we don't usually do that. And if your data is not very big, it was one of the tricks that we use a lot is called SVM. So SVM with a kernel trick, in fact, can solve these kind of problems very efficiently and very fast ways. And so, later we will talk about this a little bit. So SVM is very powerful some methods. It's like it can take into arbitrary polynomials, but turns out it's very, very and very, very efficient. All right, so what else? Okay, so I think I have talked about almost everything in the logistic regression. Okay, so this is also very important. I think this is a good time that we trying to address a very important concepts in practical machine learning. So we have idea of model validation, cross validation, regularization, all these kind of things, and assume everyone have some exposure of these kind of problems. But let's consider a much bigger or complicated questions. And what to do if the quality of our model is not very satisfying. So basically, you are not very satisfied with your result. There are 3 ways to address that. Shall we make the model more complicated or more simple? So that means if using logistic regression, I got 88% of accuracy. I'm not satisfied with that. I want to get at least a 90% accuracy. Do we need to make more complicated models? That means we're not using logistic regression. Maybe we can using various ensemble methods. Shall we adding more features, right? So for example, here, in that problems we are adding just using the sparse vectors, right? But we can engineering more features if we want. Do we simply need more data for training? Okay, so that means sometimes we only have very limited data, so that's the best we can get. So I mean, is this something that we actually need more data in these cases? That I mean, so all these questions are not obvious, and sometimes like more complicated, and models may give you like an even worse in performances. That's totally possible, which is I mean could be a problem of overfittings. And sometimes adding like new observation, new features doesn't like bring you some changes. So you have to make right decision whether you want adding more features, whether you want to add more data. Choose the right method to improve the models, to distinguish those good from the bad ones. So this is very important. These things, you have your models here, but the question is that good enough? Okay, so here, so what you can do is actually you can address all these problems partially through the validation and the learning curve. Okay, so let's load these things, and we're using this old data that we have teleterm. So we just load the data here, simple data. Okay, so so here what we do is we are going to train a logistic regression with a stochastic gradient descent. So this, and the reason that we do it is because we want to make it like more efficient. Stochastic gradient descent is more efficient than the other solvers. So what you can do is you can using SGD classifier. If you choose the loss to be log, this automatically turn into and the logistic regressions. So you have alpha. That means is my so this is quite different here. So let's see. So let's see. I think this alpha is different. Alpha and C has a different meaning here. So alpha is constant then multiplied as a regularization term. So this is different from C. C is the inverse of the regularization term. But alpha is the actual regularization term. So the higher the alpha, the stronger of the regularizations. So this is different from C. Okay, so I want to and I want you to understand this is fundamentally two different things. C is the inverse of the regularization. Alpha is the actual and the regularizations. So basically, this is from and 0.01 to 1. So the lower of alpha, the lower of regularizations. So this is kind of flipped. So here, I mean, in order to process these data sets, you have to process as a pipeline of these three pipelines. One, so standard scalar, again, we apply the polynomial features. At last, we apply this SGD and the logistic regressions. So we plot something called the validation curve, and we have to talk about this validation curve. It's basically and then the scoring that we use is we using an ROC and AUC. So basically, it's as once we vary the C values, we want to see how these and the validation error changes, and average validation error changes along the and with a different parameter alpha here. So you are getting something like this. So this is your training score, and this is your validation scores. Okay. So you can see this actually decreases for the validation scores. So probably the best alpha that you should get is right here. Right. So this gives you the highest and the highest scores here. So this shade it gives you some confidence interval. With all these that's because we're using a 5-fold cross validation, right? So this is very important. That means I have 5 different values. Then you can calculate the variances And using the variances, you can actually create the confidence levels of this and the validation curves, right? So, and you can see, and this is and quite fundamentally different. So this and value should be somewhere here. And the confidence level, that means, for and validations, you get like pretty large variances. So that's why the confidence level is pretty big. Okay. So for simple model, it's very clear the training and validation error are close and large, pretty large. And that suggests the model is underfit. That means it doesn't have any sufficient number of the parameter. So we need, and more complicated. But with the highly sophisticated models, that means that and training and validations and differ significantly right here. And this, I'm explaining the overfittings. Right, so that means, this is kind of like opposite of the C here, because this region that's like less than regularization. In this region has more regularizations. So this is kind of opposite of the C. This is due to the nature of how and history of scikit-learn is being used. So that we cannot change too much. Okay, so at last, okay, so this is also very important. How much data that we then you need to use? Of course, the more data and that you use that the beta, and the better. But well, and we need to understand whether this new data that being feeding is actually helpful. Or do we need to double the data? So there are two things, and we need to consider. If we double the data, that will be taking longer time to process, and we also collect and you need to collect more data, which is more expensive process. So what we do is, if our new data is unavailable, it's for now, and what we can do is we can vary the size of training set, and we can see how the quality of solution, and it depends on the amount of training set. So that means we are going to see how, if we change the amount of training set from 0 to 100%, and I want to see how this and the result perform, and based on the amount of the training set. So this is something called learning curve. So the idea is very simple. We will display the error as a function of number of examples using training, and basically then we gradually increase the amount of training, and we want to see how the accuracy changes, and along like once we have more and more data. Okay, so this is basically the function of the learning curve. So basically it's the same thing. So, and we take the same like pipeline, transformation, feature engineering, and using logistic regressions with the stochastic gradient solvers. So you create this learning curve with 5-fold cross validations of scoring is and using the AUC. Okay, so let's see. So if we set this alpha equal to 10, that means it's pretty big regularization here. So you can see our validation doesn't change. Has like gradually and increase a little bit. Okay, so and you can see this goes in a zigzag, and it gradually increases. Okay, so let's try a smaller one. Let's say alpha equal to 1. A 10 is pretty large, right? And regularization. And you can see 1 is pretty good, so you can see they start to increase. And these two curves start to merges. So the X is actually the training size. And each point right here means if I only using, say, like 1,000 in a training set, and I'm doing this then training score and validation scores for this kind of problems, or the fix of alphas. Okay, so this is something. I mean, for this learning curve, I'm fixing the alpha. I'm trying to see whether give me enough, and so whether it give me enough data or not. So you can see right here, it does seems with alpha equal 1, maybe like and 2,500, it's like enough here because they already reached this and the plateau here. So let's change those things to have even lower alpha here. Okay, so you can see this similar if you start to and reach the same domain here. So these things start to kind of flat out. I mean, in fact, you probably don't even need 2,500. 2,000 data might be enough here. So if you have very and the limit data set, and you can see this training and cross validation set very different. So and you can see it's like a 1 and AUC is 1, but my validation is only 0.75. So this disparity, that means it's overfittings. But if we like adding more and more data, and then these two errors start to converge and indicating the underfittings. So that means right here they start to converge at both two curves. But overall, usually the training scores is always better than the validation scores. If we add more and keep adding more data, the error on the training set will not grow. And also in this case is the error on the validation or testing data set will not reduce because the model has reached the capacity. And otherwise you change to another model, it will not make any differences. You can see this error converged, and that means new data were not helpful. This case is very interesting for business. It's possible that we can increase the size of the data set by 10, but without changing any complexity of the model. That means this additional data will not help. So that means you can bring more data, but if you keep using logistic regression in this way, it will not make any differences. Okay, so you can see this is like, and with even smaller, so alpha is like 0.05. So these two curves start to converge here. But if we move further to the right and adding more data, and maybe we can improve the quality a little bit more here. So that's possible, and you can see they still have a tiny bit trend here. But if you choose one here, you can see this already reached the plateau here. Okay, so if you're adding more and more data, it will not make any changes. So if we set in the alpha to 10 to the minus 4, so this actually shows the overfittings. So that means you can see these things start to, and the zigzag is not smooth at all. The AUC decreases on both training and validation set. Okay, so you can see this is not stable. So this just indicated, they might have some like overfitting going on. So this can give you some idea how to address the complexities of the model with new data, and this can answer like how many data And so whether I'm under this current and the parameter, whether this current amount of data is enough or not, right? I mean, if it is not, we probably need more data if needed. All right, so these are some summary here. That's basically everything I want to talk about today. We all know error on the training set has nothing to do with the quality of the model. What actually matters is the cross-validation error. What happened here? Wait, something's not right. Okay, right here. So, so basically, so what actually matters is the cross-validation error. It actually shows how well, this model can fit the data. And so the validation curve is basically, the curve of the validation and the validation error with the various different parameter here is a graph, and a graph showing the result of training and validation set depend on the complexity of the models, right? If these two curves, are training curve and the validation curve, are close to each other, and if both error is large, that's a sign of underfitting. If both curves are far away from each other, that's a sign of overfittings. So this gives you some idea and what kind of region you are living on, the overfitting or underfittings. Learning curve is actually a curve of the number of training set and versus the error. So so this is depends on the number of the observation. If again these two curves converges, adding new data won't help. It's necessary to change the complexity of the model. If these two curves haven't converged, that means far away, that means adding new data can still improve the result. So this gives you some idea to address certain problem, whether we are in the overfitting region or underfitting regions, and whether we should add in more data or not. So this gives you some idea here. All right, so that's everything I want to talk about for the logistic regression, and a little bit like learning curve and validation curve. And then this will give you some idea, and you can use that in the later of the project to give you some idea whether this is good enough or not, which is a very important aspect in the practical machine learning. Okay, so that's everything. And here for now, if you have any questions on the homework, on the next lecture, we'll talk about some other approaches for that homework problem. We will talk a little bit on that. This can help you to understand the homework problems a little bit. All right, so any questions, please email me, and I will see you on Thursday video. All right.